Now we're going to look at our third and final part of the 6.6 notes, where we'll be looking at another operation we can perform on complex numbers. And this is going to come down to something called de Moivre's theorem. This essentially deals with how do you apply powers to a complex number. So what the theorem is showing us here is that if we have a complex number in our polar form, so r parentheses cosine theta plus I sine of theta, if that complex number is being raised to any power, which is being represented by n right now, then this is telling us to take that power and apply it to the number out front, the r value. So raise r to that power, and then for the theta values inside the parentheses, multiply those values by the exponent. So the two things you're doing with the exponent are raising r to the power and multiplying theta by it. And that's it. It's just a quick, short computation, and we're going to look at some examples of that next. So here we have a question specifically asking us to use the theorem, and they've given us the number in polar form already, which is nice. We'll look at another example later on where we'll have to do some converting. Now, one thing I do want to point out is I don't see an r value here, but remember that means that there is like an invisible 1 out front. So in this case, we actually have r equals 1, and our theta value for this one is pi over 9. So the two things we need to do are raise 1 to the third power, and then for inside of the parentheses, we need to take those angles, the theta value of pi over 9, and we need to multiply that by 3. Think of it as 3 over 1 for a second, and then when you're multiplying a fraction, you just go straight across. So 3 over 1 times pi over 9 is 3 pi over 9, and it should be the same value. The theta value should never change, so it's going to be the same thing with the I sine of 3 pi over 9. Now, they didn't want us to just apply the theorem and simplify. They actually want us to go a little bit farther and then find the number in our standard complex number form. So not the polar form, which has the r cosine theta plus I sine theta, but they want to know what is the number in the form a plus bi. So we're going to simplify this and evaluate it, just clean it up a little bit. 1 to the third power is just 1. And if we're simplifying the fraction 3 pi over 9, you can reduce that as pi over 3. And again, it'll be the same thing for the I sine part. And multiplying by 1 doesn't affect anything if we were to try and distribute this, so I'm just not even going to worry about the 1 out front anymore. But I am going to go through and evaluate what cosine of pi over 3 and sine of pi over 3 equal. You might want to use your unit circle. It'd be better if you guys can start doing this from memory, though, at this point. So cosine of pi over 3 is equal to 1/2. And sine of pi over 3 is equal to square root of 3 over 2. So we have our a plus bi, but when you're typing in your answer, just make sure you put it back into the correct order, because they're going to want the 1/2 first, and then they would want the fraction of square root of 3 over 2 in front of the I value. And that's it for your answer. So now I want to look at a second example where they're asking us to use de Moivre's theorem to simplify the expression. However, this time it is not in that polar form that we need, because again, if we look back at the notes, this is set up for us to do it in polar form. It won't work if we have it in the standard a plus bi form. So we're going to have to go back to something that we did in the first section of notes here, where we need to change our a plus bi form into the r cosine theta I sine of theta. So we're going to change the form and then we'll apply the theorem to it. Since we know that a is equal to 4 and b is equal to 4, then I can say that r equals the square root of 4 squared plus 4 squared. And if you simplify that, that's going to be 16 plus 16, which adds up to 32. And that can be broken down as 16 times 2, which means The square root of 16 is 4, so you can break that out of the radical, and then the 2 stays inside the radical. You also might have noticed that this is essentially making a 45, 45, 90 triangle because we're going right 4 and up 4. So to find the hypotenuse, if you remember your shortcut rules for 45, 45, 90s, that's an even faster way to get this answer of 4 root 2. Next, we need to find the theta value. Personally, I like to use tangent of theta for this, but you can use the other trig functions if you like. So I'm going to say tangent of theta equals, so a and b are the x and y values. So in this case, y is 4 and x is 4. And of course, 4 over 4 reduces to equal 1. So what you want to do is find tangent inverse of 1. And that will give us the theta value, which is what we're interested in right now. So we're going to look at the unit circle, and you're going to find where is the tangent value equal to 1, and then your answer will be the angle for that. Now, do note that there are 2 places where the tangent inverse of 1 happens. So make sure you're looking at the original coordinate. This one's going right and up, so it's in the first quadrant. So you only want the theta value in the first quadrant, which would be the pi over 4 answer. So now we can rewrite our complex number as 4 root 2 and then parentheses cosine of pi over 4, I sine of pi over 4. So all the work we've done so far was actually what we covered in the first days of notes. So if you want to look back at those because this process is giving you trouble, by all means do so. We're only just now getting to what today's notes are about. So I've replaced 4 plus 4i with this number in polar form, but now we need to raise that number to the 7th power. So now we're actually applying the Moivre's theorem. So the exponent of 7 needs to be applied to 4 root 2. That's how we're going to start this off. Now your calculator probably will not do a good job with this. I just tested it to see if it would work or not for you guys, but it gave an ugly decimal answer, which I'm not sure that this is going to accept. So what I'm going to do is apply one of the exponent properties. You can find what 4 to the 7th power is just fine, which is 16,384. And then you can find root 2 to the 7th power as well. So you can do those two things separately. It's raising each of the 2 base numbers to that 7th power. Now root 2 to the 7th power is essentially saying you have 7 2's inside of the radical, and for every pair of them you can break one out. So that means you can break out 3 pairs and there will be 1 left over. So 2 to the 3rd power, or 3 2's multiplied together, is 8, and then that leaves a root 2 there. Hopefully I'm not going to run out of space on this. And then we need to multiply the stuff inside of the parentheses for the cosine of pi over 4 and I sine of pi over 4. We need to multiply that theta value by 7. So this is going to become cosine of 7 pi over 4 plus I sine of 7 pi over 4. So next we need to clean this up and distribute a little bit. So we are going to take the 16,384 and multiply that value by 8, which gives us 131,072. And it's that times root 2, because we can't do anything about the number outside the radical and the number inside the radical. And inside of the parentheses, we need to evaluate both cosine of 7 pi over 4 and I sine of 7 pi over 4. So if you're looking at a unit circle or doing this from memory, the x-coordinate at 7 pi over 4 is root 2 over 2. And the y-coordinate is negative root 2 over 2. So we're almost done. Now we have to distribute the number out front, that r value, times the 2 x and y coordinates that we evaluated inside. But something nice is kind of happening here, because since we have a square root of 2 that's being distributed in, square root of 2 times square root of 2 is 2. And then when you divide by 2, that just cancels out. So basically the square root of 2 and the root 2 over 2 are all going to disappear. And then the same thing happens with the second part. Root 2 times root 2 is 2. Divided by 2 cancels out. However, don't forget about that negative value. That will still change the sign of the I part. So distributing this is going to nicely come out to 131,072 minus 131,072I. So now we should be able to just type in our answer, and that should be it. And that's it. We're done. That's all for the notes today. Thanks, guys.